You know when you squeeze an empty plastic bottle and you feel that pushback? Or when you're pumping up a bike tire? Well, that resistance you're feeling, it's a direct window into these super simple but really powerful rules that govern all gases. And by the end of this, you're going to understand exactly what's happening on a totally invisible microscopic level. All right, so let's kick things off with a pretty simple question. Picture this. You've got a syringe full of air and you put your finger over the end. Now, as you push that plunger in, squeezing the gas into a smaller and smaller space, what is actually happening to all those tiny particles inside? So, yeah, this pressing question, literally, is our starting point. And to solve this little mystery, we can't just look at the container from the outside. Nope, we have to zoom in. I mean, way, way in. See, the answer isn't in the plunger itself or the walls of the syringe. It's all about the behavior of the trillions, and I mean trillions, of individual gas particles bouncing around inside. So, to get the big picture, we've got to think incredibly small. Okay, so let's put on our particle perspective goggles for a minute. If we really want to understand any gas, we need to get a clear picture of what it's made of. And believe me, it's totally different from a liquid or a solid. So here's the number one thing you need to get about a gas. It is mostly just empty space. Seriously, the particles themselves take up a teeny tiny fraction of the total volume. And that's the whole reason you can compress a gas in the first place. You're basically just squeezing out all that emptiness between the particles. And what's filling up that space? Well, it's packed with countless particles, all zipping around in completely random directions at mind-boggling speeds. They're constantly bumping into each other, and this is the important part. They're constantly slamming into the walls of their container. And that completely redefines what pressure even is. We usually think of pressure as just some abstract force, right? But when you look at it from this particle perspective, you realize it's a real physical thing. It's the combined, relentless pounding of trillions of tiny particles hitting the walls of their container every single second. Okay, so now we've got our model, right? A container full of these super fast particles that create pressure by smacking into the walls. So let's take this new idea and apply it to our original question and see what happens when we actually squeeze the container. Now, to really isolate the effect of squeezing, we need to set some ground rules. First, we're going to use a fixed amount of gas. That means no particles can get in or out. And second, we have to keep the temperature exactly the same. This is super important because temperature is basically just a measure of how fast the particles are moving. For now, we only want to see what happens when we change the volume. And this shows you exactly what happens. Look on the left. In a big container, the particles have tons of room to roam around. Yeah, they hit the walls, but not all that often. Now, look over on the right. When we shrink the volume, we're forcing the exact same number of particles into a much smaller space. They get super crowded, and the result is pretty obvious, right? They're going to slam into the walls way more often. And more collisions, that means a higher combined force, which means you got it, higher pressure. So the cause and effect here is just crystal clear. You decrease the volume, which increases how dense the particles are. Higher density leads directly to more collisions with the container walls, and more collisions means higher pressure. It's a perfect direct chain reaction, one thing leading right to the next. You know, this relationship isn't just some vague idea. It's a totally predictable rule of physics. So now, let's see how this whole concept gets boiled down into a simple but really powerful mathematical law. And there it is. So simple, right? This elegant little equation says everything. P stands for pressure, V stands for volume. And what it means is that for a set amount of gas, as long as you keep the temperature the same, the pressure multiplied by the volume will always equal the exact same number. It's a constant. This table makes it super easy to see. Okay, let's say we start with 1 unit of pressure and 10 units of volume. You multiply those, you get 10. Simple. Now, what happens if we double the pressure to 2 units? Well, for the math to work, the volume has to get cut in half, down to 5, because 2 times 5 still equals 10. What if we crank the pressure way up to 5? The volume has to shrink down to 2, because 5 times 2 is, yep, still 10. As one goes up, the other has to go down, just to keep that final number the same. And if you plot this relationship on a graph, you get this classic curve shape. You can see it right here. As the volume, along the bottom, gets bigger and bigger, you can trace how the pressure on the side gets smaller and smaller. This specific shape, that's the visual signature of what scientists call an inverse relationship. So there you have it. We've connected the dots between the tiny, microscopic world of particles and the big, macroscopic rule of pressure and volume. But this particle model, it's even more powerful than that. Let's just zoom out for a second and look at the bigger picture. So, what about heat? What if we change the temperature instead of the volume? Well, think about it. If you heat up a gas in a sealed container, you're just pumping energy into those particles. They start moving faster and faster. And faster particles are going to hit the walls not only more often, but also with a lot more force. And when you combine those two things, the pressure just skyrockets. And that really brings us to the single most important takeaway here. It doesn't matter if you're changing the volume, the pressure, or the temperature. The behavior of a gas is always about the motion of its particles. If you can just picture what those tiny particles are doing, you can pretty much predict what the gas as a whole is going to do. So, we figured out that this whole pressure-volume rule works perfectly when the temperature stays the same. But what happens out in the real world? Think about a weather balloon rising up through the atmosphere. Its volume is changing, the pressure outside is changing, and the temperature is changing, all at the same time. What happens then? Well, that's the next step in understanding the really fascinating world of gases.